Okay, thanks, Jovan. Again, this is Danielle Kennedy, and I am a research civil engineer at the Cold Regions Research and Engineering Laboratory, and that is one of our labs with the Engineer Research Development Center, the ERDC, and we're located up in Hanover, New Hampshire. Today I'm going to be discussing the use of superabsorbent polymers for freeze resistance in concrete placed using admixture-based freeze protection. So for this project, we're kind of combining two technologies of using that superabsorbent polymers for freeze resistance in concrete, but also using concrete where we've incorporated these admixtures to improve freeze protection. So it'll be kind of a lot, but it was kind of a cool project that we got to work on. And so I want to thank my team with this, and that's Dr. Ben Watts and also our lead technician, Ethan Thomas. So as I said, this is a combination of two kind of major efforts. So I wanted to give a little bit of background about cold weather concreting and what we've done at CREL for the last 30 years or so. Some research that started in the late 80s was incorporating off-the-shelf chemical admixtures in combination to be able to depress the freezing point of concrete so you could place it in colder temperatures. And as I said, this has been done for a long time, and it kind of started because there wasn't really any guidance that existed that said you could do that. All the guidance that exists says if it's below 40 degrees, you really need to incorporate a tent, heating it up, and so researchers at CREL tried to find another way to be able to place concrete in freezing temperatures. And so now it's kind of leading into this term called ARCTEC, which is additive regulated concrete for thermally extreme conditions, where we've very successfully incorporated a lot of different combinations to be able to protect that concrete from freezing above ambient temperatures of 23 degrees Fahrenheit. So your fresh concrete temperature can be much lower than that. And the way that's done, as I said, is you're depressing that freezing point, and you're also speeding up the hydration reaction. So then a little bit of background on these superabsorbent polymers, also known as SAP. They absorb many times their own mass in pure water. It can be over 100 times. And the image here shows that as more water is introduced to the SAP, it's able to grow a lot larger. And these things are commonly used in diapers, spill control, waterproofing, and it maybe has even been something that you've seen before. And the amount that is absorbed is highly influenced by the ionic concentration of the water that it's in. So if you have fresh water compared to salt water or the water in concrete, it's going to have a lot different absorption rate. As many of you know, I'm sure, concrete can be damaged by the internal expansion of water within the pores of concrete as it freezes. That frozen water takes up a lot more space than the water, so it can cause that damage by having that internal pressure and needing to expand and then crack. And so air entrainment has been used forever in concrete to be able to prevent damage. And the way current typical air entrainment measures work is they're just these uniformly dispersed small bubbles, and once they go into the concrete, they act as that void space, so when water does come into the concrete, it has a place to go and to expand. And so your typical concrete mixture is going to be about 6% by volume of concrete is going to be that air entrainment. But in colder regions where you're expecting a lot more freezing and thawing, you might have a little bit more than 6%. And then in southern regions where you don't expect as much freezing and thawing, it could be even lower. So with air entrainment, it is very useful, but there are some disadvantages. And with that void space, the more space that you have of voids, the lower your compressive strength is going to be. So that's why you really want to try to find a good balance with it. And the other downside that we've seen, especially in the lab, is that your air quantity is very difficult to control. We typically have to do several test mixtures to be able to reach that target 6% or target 7%, whatever it is for our needs. And it's especially difficult when you have other admixtures in the mixture as well. And so with this project, what we're talking about is incorporating this air entrainment technology with several other freeze protection additives. So especially in our research, we've seen a lot of struggle in trying to meet our target air entrainment. And so when the technology of the SAP came up, we were really interested in seeing if it could work for us. A little bit more on SAP in concrete to be used for freeze-thaw. Concrete, as you guys know, is very highly alkaline, and that changes how much the sap will absorb. So as I said, if this were in fresh water, it would be able to absorb, over 100 times its own size. But in this very highly alkaline material, the sap absorption is much lower. It's not fully understood, but somewhere between 5 to 30 times. And so as the sap desorbs, as the concrete pulls water and internally cures, the void space is left from the sap. So as the water goes into the concrete, you leave those voids, and that's kind of what air entrainment does as well, is it leaves those pores for water to come in and have room to expand. The sap particles do need to be a certain size. You can't just use any material, and we had to do some research and find one that was the size that fit for us. Because then when they swell and then desorb, they need to be the right size for concrete. So what we found in research is it needs to be under 100 microns. So our goals for this project were to be able to provide an alternative method to air entrainment in concrete to help it resist freeze-thaw. And with our two objectives, like I said, number one was to be able to evaluate sap as an additive for freeze-thaw resistance in this concrete that we've been working on for several years, where it already contains other freeze protection admixtures. And so we wanted to make sure it could work together, and we'd be able to kind of predict what the percent of air entrainment would be, and that going into objective number two, that we would also be able to gain strength in these mixtures as well, and we wouldn't be adding a lot of void space and lowering the strength. So our two objectives included in these mixtures with freeze protection admixtures. And number two, make sure the strength gain is adequate for these mixtures as we add more sap. So for testing, there's kind of a lot of words on this slide, but the basic thing we wanted to share with you guys is the range of sap was something we kind of had to figure out with this. And we were targeting a 6% swollen sap by volume, but the exact absorption is not really certain. And so it was estimated to be somewhere between 5 milliliters per gram to 45 milliliters per gram. And so for this test study, we tried 4 different dosages, assuming absorptions in that range, starting at 7.5, going to 15, 30, and then ending at 45 milliliters per gram. Again, and that's because that absorption of the sap is really not known. And so we had to test out all these different ranges. And as I said, we're combining this with those freeze protection additives. So we're mixing and curing this concrete at 23 degrees Fahrenheit, and it stayed in that cold space for 28 days. The mixture that we used as our control and that we incorporated all these sap into was a mixture that we had had a lot of success with during our previous study of using these off-the-shelf admixtures. And it's a combination of a non-chloride accelerator and a corrosion inhibitor. And our goal here was to use less than the manufacturer's recommended dosage, so you're not adding, gallons and gallons and gallons of admixture. And so our baseline was a mixture that was 50% of that manufacturer recommended, that we had a lot of success with in a previous study. And then the concrete mix was pretty standard. It was a 7-stack Portland cement mix with a 0.42 water to cement ratio and a 3/4 nominal aggregate size. So in addition to those 4 dosages that we made, we had 2 controls, and so 6 mixtures total. And those 2 controls were one that had your typical chemical air entrainment, and then a mixture that had no air entrainment at all. The testing that we completed was for compressive strength. We did a 7, 28, and 90-day strength testing. And then for modulus of elasticity, which you can see in this image here, we did testing at 28 and 90 days. And then we did testing for freezing and thawing following ASTM C666. And we followed the B method, where your samples are frozen in the air and then they're thawed in the water. And we followed these all to the specification, except for mixing and curing in that cold environment, in that 23 degrees Fahrenheit room. And we did not moist cure, because you can't moist cure when things are below freezing. Moving forward into some of the results, these are our compressive strength results. And moving from left to right, that's where our controls were. And as you can see here, there was, as we added more sap, which you can see from left to right, 2.25 pounds per yard, all the way up to 14 pounds per yard. You can see that the strength at 7 days especially is gaining over time as we added more sap. So it's stronger than the control, even as we add more sap. And then in addition, our 28-day strengths were pretty comparative to the controls. So as you can see, there's still a gain at the 90 days as well. So that's the gray is the 7-day, the yellow is the 28-day, and you can see a pretty large growth at the 90-day. So the one mixture that we saw, pretty comparable to the control and not a lot of huge strength gain after 28 days was our lowest dosed sap mix of the 2.25 pounds per yard. And we'll go a little bit further into that as we see some more results. These are our modulus elasticity results. Not too much to report here, but again, our values at 28 days and 90 days were, comparable to the control, more than the control at 7 days in most cases. So this was just a test we run pretty standardly, and there's not always a lot from it, but these were acceptable results to us. And then moving forward into our free spa testing results, this was, again, ASTM C666. And the way this test is measured is all specimens at the very beginning, before they're put into the chamber, are measured for their relative dynamic modulus. And once they reach 60% of their original, they have failed. And then if they continue to stay where they are, they'll go until it's been 300 cycles of freezing, thawing, freezing, and thawing. And so as you can see here, our numbers were switched a little bit, but our lowest dosage, which was at 2.25 per yard, here failed at just over 100 days. And going up here to the top, if you can see my mouse, our control that was air entrained stayed here at the top with this black line. You can see it did pretty well with this testing. And our control that did not have any air entrainment failed just before the 300-day cycle. So even though it wasn't air entrained, it had those freeze protection additives included in it. And so it lived to be over, 275 days, which is pretty strong. But all of our other sap entrained mixers performed pretty well for this test, with our only one failing being the lowest dosed sap. And as I said, the strength for 7 and 28 days and 90 days for that mixture, it didn't really gain very much over time either. So moving into kind of our key observations, we saw that sap is capable of providing concrete with resistance to freezing and thawing without having to use air entrainment. And also works in combination with these freeze protection additives when you're carrying it at 23 degrees Fahrenheit. So what we saw from the strength results and from the freezing and thawing results was that it is possible to have not enough sap. So there's just not enough voids, and 2.25 was the lowest amount that we tried. So we could try another value higher than that, but lower than the second highest, and see if we could find, a threshold of where it's just not enough. But what we found from our small scale research was that lowest dosage of 2.25 pounds per yard was just not enough. And as I said, as you move more into the 3.5, 7, and 14 pounds per yard, we saw that there was an improvement over the control for the 7-day compressive strength, and then again for 28, and then on to 90. So as you're learning about this, you may be interested in, what's the cost? And when we did this study, it was a very small laboratory study, so we got a small sample volume pricing. And for adding 3.5 pounds per yard, it would add about $26 per yard of your concrete, which, as I said, this was a sample volume pricing. If you wanted to go larger, it could be cheaper. The other thing we wanted to note with this research is, it's a combination of a couple of strange things, these polymers to be used as air entrainment, and also placing concrete in freezing temperatures, which is not a very typical use of concrete. And so what we wanted to mention with this is, although this is very niche, this combination could be very useful in a cold region where you need placement soon, and you don't have time to do a lot of different testing batches and doing samples to try to see what your strengths would be and make sure you can hit your target air. The point of this research was you have a patchwork or you have a small placement and it needs to be done now, it's cold outside, and you've got to hit that air. So that's kind of the results we found from this test. We found to be very successful. Moving forward, some of the things that we could add to this small research study would be trying this with different combinations of those freeze protection additives. This was just one dosage of the freeze protection additives for the 6 mixtures. And, we are from the cold regions lab, and so we always want to go colder. This works at 23 degrees Fahrenheit. Does it work at 15? Does it work at 10? And then in addition, we did just try one sap product for this research. And So just some additions we could make in the future going forward is just having a few different variables and seeing how this SAP performs with the freeze protection additives. And so that's all I have for you. If Giovan's got some questions, I'm happy to take those as well. But thank you. I'm really glad we could kind of do this virtually. I know it's a little different, but hopefully we can all get together at ACI next time.
Thank you, Danielle. A very, very interesting talk. We do have some questions already, I think. Okay, the questions are not really related to research. Okay, the first question related to research is, did you do any testing related to shrinkage and temperature cracking?
For this research, no, we didn't. This was a very small kind of learning study, and we did not incorporate that this time.
Okay, second question is, did you determine effects to slump? Yes, effects on slump.
We did slump testing in the very beginning, and it was kind of difficult to dial in what the slump would be. At some points, it would be, you know, a full slump, but it was still very workable. And we were working in a cold space, and so you want something that's very workable and not going to harden immediately. But slump was not our number one goal with this. It was trying to hit that air entrainment target, which sometimes, as I'm sure a lot of you guys know, it's hard to meet your slump and your air entrainment when you're working with a combination of different admixtures. So we did focus on slump and work with it, but that was not our number one goal.
Okay, thank you. The next question is future plans. Sorry, this keeps on scrolling. Future plans, you mentioned, in your future plans, you mentioned colder temperatures. How cold is needed for different applications?
It really depends. So at Krell, we do a lot of research on when you are in areas where you don't have a lot of access to typical materials and you are in the freezing cold. We did some research back in January up in Goose Bay, Canada, where it got down to 0 degrees Fahrenheit. And so it really depends. And of course, this could be more applicable to military applications. I know on the civil side of things, you're going to keep things around 40 degrees Fahrenheit, maybe a little lower. But this is a lot more for military application, or it could be, where you don't need to carry your chemical air entrainment. You could just have this bag of, you know, this powder that turns into sap and when it's moist. But as cold as we can go is also always what my supervisor says. You know, how cold can we go? How useful can we make this? So we've done some successful research with the freeze protection additives without sap down to 10 degrees Fahrenheit. So at least that.
Okay, I think there's a follow-up questions to that. So can we use this in deep water construction, and up to which temperature can we use this?
I am not an expert on that. I would have to defer and say I'm just not sure. And I can talk to the folks at my lab that I do research with that may have a little bit more experience with that. Yeah, as for deep water, I'm not sure. We're definitely comfortable going well below freezing. I can't put a number on it at this time, but that's an interesting topic and maybe something we should look into.
Okay. The next question is, how do you explain the difference between the non-air entrained concrete and the concrete with the lowest SAP dosage?
Well, the one that is non-air entrained, it was about 2% air entrainment in it. And the difference between those is the one that's non-air entrained, if there are any bubbles in it, they're not, you know, perfectly sized, they're not spread out adequately. And so the way SAP helps is these are perfectly sized spherical bubbles that give, you know, the water a place to go and expand in those pores. But when you're not using chemical air entrainment or any type, and it's just the air that's entrapped inside of the concrete, they're all different size bubbles and they're just not correct or enough air for producing a space for that water to go and freeze.
Okay, thank you. The next question is, did you notice any segregation or bleeding problems during mixing using SAPs?
No, not really. And as I said before, these mixes were pretty, you know, slumpy, for lack of a better term. They had a high slump, but we didn't have any problems with any bleeding or segregation that we could see from the research.
Okay. One of our attendees is asking, how can they obtain the full mix design for all test specimens?
We are working on a publication right now that we're pushing out, and I don't know if people want to reach out to me via email or follow me on LinkedIn, and I can keep them updated there. But we're working on getting this kind of published in a journal, and we're working with our sponsors now to kind of get that out, so this can be something people can use and read up on.
We have some more time for questions. So another question is, do you think that SAPs can be used with SCC mixes?
I am not an expert in that category. I don't want to say the wrong thing, but from our experience with the SAP, we really didn't do much different than we would for a typical concrete mixture in our cold rooms. And maybe the time that you add the SAP would be a factor. But I mean, this research showed us that it is useful for, air entrainment, and it is comparable to chemical air entrainment. So I would venture to say yes, it's definitely worth looking into.
Okay. And the last question is, let's see, we have a few. So I guess this is probably you just having to reiterate some of this information that was stated, but what percentage of SAPs have you used, and what are the potential applications for this material?
We tried 4 different dosages, which I'll go back and say those, and these are all based on the volume of the concrete as well. So the dosages we tried were 7.5 milliliters per gram, all the way up to 45 milliliters per gram. And the equivalent concrete dosage to that is about 14 pounds per cubic yard for the lower end, and about 2.25 pounds per cubic yard on the higher end. And some applications for this, as I said, this is very niche. We are combining additives to place this in cold temperatures with SAP to be able to not have to use chemical air entrainment. So applications for this would be, you're in a cold environment, you have a patch on, I don't want to say specifically a runway or a roadway, or just wherever you'd have a concrete placement, maybe a slab where you don't have time to wait and it needs to be placed and it's already cold temperatures, it's below freezing, and you also don't have the means or the time to test a bunch of different sample mixtures to get your air entrainment perfect with a typical chemical air entrainment, and that this SAP could be used in place of that. So again, a very specific placement for this, but that's why we're doing it, because it's just kind of a cool research study where we're able to combine this technology that we're working with these freeze protection additives and just adding a new test to it and seeing if we could use SAP in it. So again, it sounds really niche, but it could be useful.